3 more weeks, class, and then the finals week. So today is our day to transition into the integration, which is the second part of calculus. I guess we sort of did it with antiderivatives, but today is the one day we're going to do something. Remember when we did derivatives, we spent like 2 weeks doing something called limits. We're going to do something sort of similar. We're going to do something we're not really going to directly use anymore after today. But fortunately, there's only 3 homework problems that you have to worry about with all of this. And I'm going to do 2 examples that really relate directly to those homework assignments. The way this textbook does this part, I thought was kind of brilliant. It kind of helps understand it without going into something else. So if you've had any kind of calculus before, you've probably done something called Riemann sums. Okay, you divide it up. That's basically what we're doing, but as I looked over it, I didn't hear them really calling it Riemann sums until like into it. They just kind of did it. So this will help us lay a foundation for what it means to take an integral, what it actually means, and sort of this is the way they would have done it 50, 75, 100 years ago before they had all these calculators. But as you're going to see, we're going to hopefully make a connection between what we're doing today and the antiderivative. We'll put that together on Wednesday, and then that will be the last of our new material for exam 3. Have I posted a practice test yet for exam 3? I'm not sure if I think I have it. I think I got it over the week. Anyway, if I haven't, I will do that soon. Friday will be a review day. Well, I guess I should click here. So we're here at 5.1. Today, which will be kind of building the foundation. 5.2, we'll actually get into doing an integral. And then after the test, we've only got 2 sections. We'll find some specific uses for that technique. So we've got a review on Friday, and then our exam 3 will be on that Monday. Okay, then we'll do 5.3, but I'll also look to do something like to do a video. Some of you might be traveling over the Thanksgiving and such, so we'll do maybe a little early video on it, but I'll be here. Okay, so we're going to start off with an example rather than try to say any sort of theorems or concepts or anything, because basically all you need to know is geometry. How do you find the area of a rectangle? Area of a rectangle? Length times width, base times height, however you want to, you multiply the 2 sides. You can do that, that's all we're doing today. But we're making different rectangles, and we're going to see it helps us estimate the area. Okay, so if you've got a shape, you can always put a rectangle in there. Rectangle's easy to calculate the area of, even if the shape might be kind of strange and you can't get it exactly. What we're going to do is find ways to make it that the estimate could be better and better. That's all we're doing. So we're going to start off with this example, a distance problem. You're driving a car and your odometer's broke, so you don't know how far you're going. I've had cars like that. Usually when the odometer's broke, the speedometer's broke too, but whatever. Let's say our speedometer's still working, so what we do is every 30 seconds we record the speed on the speedometer. And then we take several of these readings. Let's say we do it every 5 seconds, we record another one. Over a 30-second time interval, we're going to make 5-second recordings. And this is the table we come up with. So first we are going 17 miles per hour. Hopefully we're having our friend do this, so we've got our eyes on the road and we're not going to, run over somebody or something. 5 seconds later, clock ourselves at 21 and so forth. So that's the data. Notice that's in miles per hour because that's what our speedometer gives us. But since we're talking in seconds, wouldn't it be nice to have this sort of in seconds? And so on the fly, we had converted to feet per second. I think this is, yeah. So we see the velocities have magically been converted for us to feet per seconds. So it's just kind of trying to give us a real situation, how we would do it, and then we would need to probably convert those into feet per second to make the calculations that we're going to do next easier to do. And then we could convert those, what we come up with, back into miles per hour, I guess, or if we needed to get our speedometer to work, but we're really not going to do it. So what we're going to do is we're going to graph these points on the graph, and we're going to use the left endpoints, so the left side endpoints, to make our rectangles. Okay. What kind of a graph is this, or what kind of data is this? What's that? It's variable, but what kind of a variable are we dealing with? What is a reading of miles per hour? What kind of a variable is that? A rate. Good. So I know I'm fishing here it's a rate. It's an average, and again, actually it's an instantaneous rate of change. So we could actually, the data we have are derivatives, derivative data, right? It's a slope. It's a rate of change. So this graph, if we were to kind of connect it and say that maybe we're smoothly accelerating and decelerating, could actually be a derivative curve, right? That's really what we're dealing with. And what we're going to do is we're just going to see what do we get if we make these rectangles. So I start from this. Oh, I've got my data up there. Yeah. So I start from this one, and I make a little rectangle here. How wide is this rectangle? It's 5 seconds, right? 5 seconds wide. In fact, actually, if I do it this way, where I've got my dots here, how wide are each of these rectangles going to be? 5 seconds, which is the nice thing. So their bases are all going to be the same. Their heights are going to be slightly different. And again, they're going to be based off of these left-hand points that we've come up with. Notice I'm going from the left towards the right, which suggests that maybe the next time I'm going to do this, I'll go the other way, because what we're going to see is we get generally either an overestimate or an underestimate depending upon which way we go. So there's another rectangle, and then I come across here. So notice I'm starting at the left side, going to the right, and I get another rectangle. All of these are going to have a change in x of 5 seconds. So think of this as we go forward. This is our dx. We're multiplying by the change in x. But if we multiply time by rate times time, what is that going to give us? Think more general. There's a formula, right? What's that? No, that would be the second derivative. So if we took the derivative of this, we'd get acceleration. This is our velocity, or our speed. But if you take rate times time, you're going 55 miles an hour for an hour. How far have you gone? It's going to give us distance. So each of these rectangles is actually an estimate of how much distance we've covered in those 5 seconds, right? Because we've got distance times rate times time. So distance equals rate times time, and that's exactly what we're doing here. Okay, so I'll just kind of keep going this way. This one's a little higher. And then notice we don't use this last point because we're starting with the left ends and we have 1, 2, 3, 4, 5, 6. 6 different rectangles. 1, 2, 3, 4, 5. Oh, this thing's in the way. 1, 2, 3, 4, 5, 6. Okay, so we've got 6 rectangles. These are the heights of the rectangles. So if I take 25 times 5, I'm going to get the area of this angle, of this rectangle. Okay, does that make sense? Okay, so I'm not doing anything overly fancy or anything. That's all we're doing. And then once I get that, if I add that to this rectangle, which is what, 31 times 5, if I add these together, I'll have the distance I've covered in the first 10 seconds. Yeah, first 10 seconds, right? Each of them has a base of 5. And the heights I'm taking from here. So this one's 31, this one's 35, a height of 35, 43, 47, and 46. Okay, and actually your problem is going to be very similar to this. They give you might have to convert the table. I didn't look real closely if they gave it to you in feet per second or whether they gave it to you in miles per hour. You might have to convert it first, but you'll basically do this same thing. So 25 times 5, 31 times 5, plus 35 times 5, plus 43 times 5, oops, not 15, times 5, 47 times 5, and plus 46 times 5. Since you're multiplying everything by 5, if you wanted to, you could actually add everything together first and then just multiply by 5 at the end. That might be the easier way to do it. In fact, I think that's the way I'll do it, just to make it a little easier. So we end up with, so we have an answer here. So I'm taking 25 plus 31 plus 35 plus 43 plus 47 plus 46. That totals, so I'm gonna, and the book uses this summation, right, of the f of x's, or f of t's, right, the velocities. So then I multiply that by the base of 5. And I come up with 1,135. And what I found is really I found two things, sort of. I found the area underneath this curve. So if I thought of this as a function curve, that I got a few data points, and maybe that was my data. I've actually got the area under the curve. You can see it's a little bit of an underestimate, right? Because these are the pieces I'm missing. But then actually when I get to the other side, I've got some sort of surplus going on. So over here I have a little extra. My estimates are a little over. So a little under, a little over, you know. Again, it's just an estimate. How could I get a better estimate?
I found this on the web.
My watch was going to answer. How can I get a better estimate? How could I reduce that over or under? Yes. Make more, yeah. So more and smaller. So if I make them smaller, so I could do it. I have 6 here. If I did it with 12, they would be half this. They'd be slimmer. I'd be having a base of 2.5, and there would be just less slop. We'll put it that way, that technical word, right? And we'll see that. And that's basically what we're going to do is then we take the limit and we take like 1 million of these. That's a lot of calculations, right? But we're going to see that in the end, there's a real simple calculation we can do where it's only 2 calculations and it will give it exactly the value we need. We start picking that up after the test. So, but it has to do with the antiderivative. So we find the antiderivative, we look at the beginning and end of the antiderivative, and that's going to give us the exact value without having to do 1 million calculations. Aren't you happy for that? two calculations is a lot more doable than a million. So we okay with this? And then again, your homework will ask you to use left endpoints, then it will ask you to use right endpoints, okay? Because this is, again, the way the technique was, because this will give us a different type of an error, right? Maybe either over or under the other way. So if we're going to use right endpoints, we still see the same rectangle that is 5 seconds wide, but we go backwards from the right. So this becomes our rectangle. We go backwards this way. So this gives us a right using the right endpoints. And notice we used the last one, but we didn't use the first point. We didn't use the 25, but we made our rectangles with these points. And again, we could go through this. Again, they're all times 5, so I would just say, let's add these together. 31 plus 35 plus 43 plus 47 plus 46 plus 41, and then multiply everything by 5, because here's the 5, and the width up, or the height of it is, in this case, 31. This one is 35, and so forth. And we'll see, we'll get a slightly different number. So I come up with, when I add all the heights, I get 243. And then when I multiply that by 5, that will give me the area of all the rectangles added together. And I get 1,215, which again is a little bit more. 1,135, 1,215. And there's another method where you take both the left and the right, and then you average them, and you figure that one's over and one's underestimating at some place. So that's a little bit, you get halfway between there. That's a pretty good one. Another method is to do what they call a midpoint. So you find the halfway between where you want to draw it, and sometimes that's a little bit better. You get a little over on one side on the other. And again, couple that with making a lot more rectangles, you get more accuracy. Okay. So this is an example where we just had some data. We didn't have a function, and we could do this. So it's a technique you might use at some point. We do call these Riemann sums, because I guess Riemann came up with this idea of area under of a curve, just make a bunch of rectangles, and we can get as accurate as we need to get if we just take more and more, smaller and smaller, more and more rectangles. So that's one of the homework problems, and then you'll have 2 homework problems where they'll actually give you the function, and then you have to get it under the curve. They don't give you the endpoints, so you're going to need to use some, at least this is the way I would do it. I would use a technology to come up either with a table of values or come up with the endpoints. So this is just the idea that you came up with. If you take like this one, the area under this curve, the rectangles are going to overestimate the area, right? But if we have more rectangles, the overestimation is a little bit less, right? So that's all that's showing. And this is if we do what we call right endpoints. The rectangle is based off of the right side, and then it goes backwards. If we couple that with, I forgot to take this. This should be saying left endpoints. I copied it, but I forgot to change it. Left endpoints, and we do the same thing. The more rectangles we get, the more accuracy we're going to get. And then again, we could do an average between the left and the right and get even probably more accurate. Okay. So these types of problems, what they're going to give you is they'll give you a function, which is coming here. So something like this, and they'll say use left endpoints and 4 rectangles to find the area under the curve from 0 to 4. Okay. So what we need to do is then the rest is for us to set up. Okay, so after what I'm going to show you, this is what I did. So what I did, I went to Desmos and I graphed it. I did the graph. Notice I've got my my intervals going from 0 here to 4 here, so I can basically forget anything out here. Okay. 4 rectangles, well, that's kind of nice. So that means there's 1, 2, 3, 4. They could have asked for 5, and then you're off. You're using some decimals. But this was nice. If it's 4, then I'm going to have one rectangle here at 1, another at 2, another at 3, and then the last one at 4. If I'm going to use the left endpoints, I build my rectangles from the left over. So this one would look something like that. This one would look something like that, look a little bit overestimation. A little bit over like that. And by the way, there's 2 questions that are very similar. They just give you different functions. But you'll be doing the same thing, and it's just the calculations. We just need to find the endpoints and the width of the intervals. Now with this one, what's our width of our rectangles? 1. Isn't that nice? Multiply by 1, it doesn't change anything. So the width of each of these is 1. So all we have to do is add the values using the left endpoints. And so this left endpoint was 25, then there's a 24.5, 23, 20.5, and we don't use the last one because that's an extra point because, yeah, we didn't use it. So again, all we're going to do, and all I did is with Desmos, I put a table in and I said, I put in the x values of 0 through 4, give me the y values, and let me go through this. If you want, I'll show you how I set up the Desmos to do it. You can also do it with the TI calculator going between table and such. So, but the main thing is I'm going to use these endpoints. So I take 25 plus 24.5 plus 23 plus 20.5, and that's 1, 2, 3, 4. So I know because they asked for 4 rectangles. So those are the heights of those 4 rectangles, right? I multiply by the width of those 4 rectangles, and now I'm going to get the area. And again, think of it, you would really do it one by one. You get the area of each rectangle and add them together, but this does it as well, right? So you don't have, whatever the width is, you're not having to multiply repeatedly. So we add those together. So as long as you know how to add and multiply, you can do the homework real easily. It's just a matter of getting it set up. But the thing I want you to focus on is we're getting the area under the curve this way, and that we're really just doing it by finding areas of rectangles. And then what we're going to do is we're going to say, okay, if I made 1 million rectangles and made them really small, I'd get really accurate. That's what we're going to be able to do. And there's some sort of magical thing that there's this connection. And it makes you start to believe that, wow, our world really does make sense. At least the mathematics make sense, the physics make sense. I don't know about human society making any sense, but certainly the physical world does seem to all be connected to something, right? You see, and that's kind of nice that we can rely on it. We don't have to worry. Some of our ancestors were worried about whether the sun was going to come up the next day, but when we understand how things work, we stop worrying about that. Of course the sun's going to come up because that's how things work, right? Because there's all these nice patterns within the mathematics. And the mathematics is just a reflection of what's going on in the world around us. So it's just 93 whatevers, whatever the units are. That's the area under the curve. And remember what this is that graph is a derivative of some sort. It's a slope graph, and so it's a rate of change. The area underneath that curve is going to be the accumulation of those rates. And so what we're going to see, just like in the last one, when our accumulation is speed and time, the accumulation is distance. Again, this might be an example of a hose filling up a bucket. And so what we've just done is, after getting, if that's seconds or minutes, after 4 minutes, we could say, well, we've got 93 gallons of water in our bucket. Literally, we could do that. And all we needed to know is how fast is the water coming out. We are not measuring the water, we're measuring the rate the water's coming out. So this is kind of cool. If we can measure the rate, we can also use the mathematics to give us how much do we got. Okay. That's the math we're going. So it's kind of backwards of what we did. What's that? 90. Did I get it wrong? 25, 24.5, 23. The number is the number. Where did? Oh, this is in what section? Sorry. Oh, we're finding the left-hand points. Yes. So I start at the left, which is 0, and I find its y value. So I'm finding the function value. So yeah, good. Function value at 0, function value at 1, function value at 2, and then the function value at 3. That's all I'm doing. Yeah. So I could plug in 0, 1, 2, 3 into the function, get those values, and I don't even have to draw the graph. But if I draw the graph, I understand physically what I'm getting. It's an accumulation. Okay. Is that okay? Okay. And then the next one, again, this is kind of use the right endpoints. Okay, so we do the same thing, same picture, right? Same points. It's just that when we come to make these rectangles, we go the other way. So we start from the right end, and notice we get a little bit of under. We go from the right end. This one goes from the right end. And then this one goes from the right end. And so, yes, we're doing, notice we're doing the function value at 1, plus the function value at 2, plus the function value at 3, plus the function value at 4. That's going to be the heights we use for our rectangles. And so if we read that, it looks like 24.5, 23, 20.5, and then we do use the 17. We don't use the one on the far left. We don't use that boundary point. So because we just use these 4, and then again, we multiply by the width, and each of these still have a width of 1. We didn't do anything more. Now, one of the questions we'll ask you to do, I think the last one, it says do it with 5 intervals, then do it with 10, just to get you to see it's going to be more accurate. It's not too much, just kind of plug these in, get your table, and you're good. Okay, so we get that one. So you understand the difference between the left and the right. One of the questions we'll ask you, and I'm not going to work this all the way out because it's just that, is actually this one is supposed to say use the midpoints, I think. And again, I forgot to change the instructions, but you'll see I do the same thing, but now the points are different. I'm halfway through the interval, so I'm not at 0 and I'm not at 1, I'm at 0.5, and I'm at 1.5 and 3.5 and 2.5, so I'm at the midpoints. And notice I just have the 4 points, and so what I do is that's the midpoint is going to be my rectangle, and I get a little bit of both, over and under estimation. So this one makes for a little bit more accuracy. And again, one of the questions we'll ask you to do this. So I'll show you what I did with Desmos. I'd like to say you're not going to have to do this on the test, but there might be. I haven't seen the test, so I don't want to, And again, the widths are all still 1, so we're just really with the midpoints, we're finding the function value at 0.5, the function value at 1.5, the function value at 2.5, and then the function value at 3.5. We're going to add all those together and then multiply by the width. Okay, and what you'll see is as we get to here, this is our change in x, the width, and so you'll see that become a dx, and so that's where that's coming from. So 0.5 gives us, again, 24.875 plus 23.875 plus 21.875 plus 18.875. Add all those together. Those are all the heights. Multiply by the width, and that will give us the area under the curve. Okay. So there's 3 problems in WebWorks. Very much like this. 2 of them have a function they give you. So then you go, and if you'd like, let me show you how I used Desmos. We can discard that stuff. And again, you could do the same thing. What I would do is I'd put in the function, and I like to do it with f of x. What was it? It was 25 minus 1/2 x squared. So you get your function. You can kind of set up your window based upon what you have here. The other part is I add in the table, and this was what makes it all easier to do. I change the x1 to x. I change the y1 to f of x. And then whatever I want my intervals to be. So like that, say for that midpoint one, I calculated from 0 to 4. If I'm going to do endpoints, they're going to be 0.5. I would just enter those in. 0.5, 1.5. And notice it's plotting them on me, so that's what I did, and then I took a screenshot of them. 2.5. So just figure out where those endpoints are. And then it even starts suggesting 3.5. Yeah, I don't need 4.5. But then you get your heights of your rectangles, multiply by your width. So it's just a matter of what is my interval, how many boxes do they want? Divide, if it's 5, you take your interval divided by 5. That tells you how it is. And you just come up with a table like this. Do it a couple times. Now, if they want double, we just might have to add in more points, right? So what's the goal behind this whole activity, though? Not that you become real good at doing Riemann sums, because we're not going to do much more after this, but that you understand what we're getting is the area under the curve, and that this is a precursor to the integral, which is what we're going to do. So remember, each of these, what they're giving us is a derivative, and when we get the area under the curve, the way we get that is we use the antiderivative and the 2 endpoints, and we're going to get it. We're going to get the same value as if we did couple million Riemann sums. Okay, so that's what we got today. We'll talk a little bit about indefinite intervals on Wednesday. That will be it for the test. Wednesday we'll go into the review, and I'll be posting the review for test 3 here momentarily, hopefully maybe over office hours. All right, good.